So, all right, welcome to Math 150. This is lecture 12, level sets and special coordinates. The vote has been overwhelming that the first exam will be Monday, March 13th. We should basically be finishing the material now. This means there will be a decent amount of time between now and the exam. You should be reviewing it. You should do practice problems, look at, I think I moved this up for some reason. All right, I'll fix that later. All right, so what I want to do is I want to start off by talking today about some of the special coordinate systems. Then I'll backtrack a little bit to level sets. And so the first one the book talks about is cylindrical. And so cylindrical is something in free space. The name really describes what it's going to be. It's going to be related to things that are cylinders or have cylindrical symmetry. And so the three standard variables in Cartesian coordinates are the x, the y, and the z. And in cylindrical, we have x, y, and then we just have z along for the ride. So x is our cosine theta, y is our sine theta, z equals z. So essentially what this is it's just taking your polar coordinates and so the polar coordinates was just, x equals r cosine theta, y equals r sine theta, and then the inverse would be r is the square root of x squared plus y squared, and tangent of theta is y over x. And so what's going on over here is if this is my x-axis, this is my y-axis, and I give you some point here, I can write this point as x comma y, or I could write it as r and an angle theta. And the idea is, depending on what you're doing, sometimes one coordinate system is more convenient to look at than another. Okay? If I give you x and y, is it easy to find what r and theta are? Do I have a way to convert from one to the other? And if I give you r and theta, can I find x and y? So the next question is it unique? If I give you an x and a y, is there one and only one r and theta that works? And conversely, if I give you an r and a theta, is there one and only one x and y that work? So what do you think? All right, so what's the issue?
You could have like the theta of dy to get there.
Good, so if I allow r to be negative, I could go all the way down here for my r and then choose my theta to wrap all the way around. So we often put some constraints. So we'll often say, r will be greater than equal to 0, and maybe 0 less than equal to theta, maybe strictly less than 2 pi. Because if theta was allowed to be 2 pi, we could wrap around. Is that enough to give us uniqueness? Does each r and theta give us one and only one xy? Does each xy give us one and only one r theta? I'm sorry? So r is the length. Right. So what it's basically saying is, hey, look, choose an angle and then choose how far out you go. So if I give you point xy, xy has a specific distance from the origin. It's got a specific angle. Is there any point where I might have a yes? Yeah, so if I'm at 0, 0, the distance is 0, but any angle would work. So there is a slight breakdown. So at 0, 0, actually any theta would work. But other than that, it's going to be unique. And the only difference between cylindrical coordinates and polar coordinates is that for cylindrical coordinates, we allow z to be in the game. And we're just moving straight up and down. So it's not a real big deal like that. So if you want to specify where you are on the Earth, you could specify your latitude, your longitude, and how far you are from the center. This is the spherical coordinates, which we'll get to later. Or you can give your x, y, z coordinates. Depending on what you have, some things are more convenient than others. Okay, so the next is, why do we care about this? So whenever you're trying to extend what you already know, there's always a danger that the case you've study that you're building your intuition from might be so simple, you don't actually see a lot of the complications. When we do limits in one dimension, well, there's really only two ways to approach a point. I can walk up to it, or I can fall down to it. I'm approaching from the left or the right. In several dimensions, I can spiral, I can do any kind of path that I want. There's a lot more freedom. So there's a lot of things that we just can't see in one dimension that are going to emerge and be fundamentally new once we start doing multivariable calculus. So when we're looking at regions that we want to integrate in one dimension, what's the only region you ever integrated over in one dimension? Okay, but what kind of shapes? Line. That's it. One-dimensional integration, you always integrate over a line. For 2 dimensions, I can integrate over any nice 2-dimensional shape. What are some possible shapes? Square. What else? Circle. What else? Triangle. Yeah. This is not a hard question, right? Congressional district. You can take any strange shape you want, right? And we can talk about integrating a function over that. And now an interesting question, which we're going to get to in great detail later in the semester, is if you had your choice, you would clearly choose, I want to integrate a nice function over a nice region. Life's not that good. Which is better, to have a nice function over a complicated region or a complicated function over a simple region? And it turns out for a lot of things, it's much better to have the nice region than the nice function. So I am going to assume if I give you, for example, a circle of radius r, and I want to draw it in Cartesian coordinates, this is not going to be a shock that it's going to look like, well, okay, my outlook is terrible, but this is not going to be a shock that this is the equation of a circle of radius r. And we could write this down as it's the set of all xy such that x squared plus y squared equals r. This would be the boundary. Or if I wanted to be filled in, I could do all xy such that x squared plus y squared is less than or equal to r squared. And this would be, filled in. Okay. Now remember, we have our coordinate transformations. X equals r cosine theta, y equals r sine theta, or r is the square root of x squared plus y squared, and tangent of theta is equal to y over x, which is the same as theta is the arctangent of y over x. So this is what everything looks like in xy space. What do you think it's going to look like in r theta space? What is the equation of a circle going to look like in r theta space? Yes. Yes, it would just be the same. It would just be, it's the set of all r and theta such that r equals r. And that would be the boundary. And so here is my circle of radius r. If I want to fill in, it would be all r theta such that r is less than or equal to r. And so in that case, here's r, here's theta. What kind of shape is that? Rectangle. So a circle in Cartesian coordinates looks like a rectangle in polar coordinates. Rectangles are much easier shapes to work with than circles. If you want a nice challenge, come up with the formula for the area or the perimeter of a circle. The ancient Greeks had this. They had the formula for that. They had the formula for the sphere. It's amazing what they were able to do. Archimedes was damn close to getting calculus with his method of exhaustion by taking inscribed and circumscribed regular polygons with more and more sides and looking at what happens and getting pi and all the stuff from this. But the whole point of these coordinates is that rather than working with a circle, I'm now working with a rectangle, and that's a lot easier to play with. Right? Do we have any physics students here? You need to be extremely careful because a lot of times the physicists and the mathematicians have different notation. So have you done spherical coordinates in physics yet? So the real question is, what do we need to describe where something is in three-dimensional space? Well, we could do it with x, y, z. We could do cylindrical coordinates, r, theta, and z. Another one is the spherical coordinates, theta, phi, and rho. And there is a reason why we're using rho and not r. We'll see that in a moment. And we've made the z-axis a little bit special, and we come down some angle from the z-axis, and then once we come down, then we just spin around. So if we're looking at what's going on, rho is always going to be greater than or equal to 0. It's how far out we're going from the origin. Then phi is how much we're coming down from the z-axis. So how far down can we come from the z-axis? What's the range of phi? So we'll clearly have 0 less than or equal to phi. How far can phi go? So we're coming down from the z-axis. How far can we go down for phi? I'm sorry? Well, so we're starting off when phi equals 0, we're pointing up in the z-axis. And then we start coming down by phi, and then eventually we'll come down to some angle, and then we'll spin around, and we'll get a circle that's parallel to the xy plane, but raised a little bit. And so the question is, how far can phi go down? Could phi go down 8 pi? You mean upper bound for? So one possibility is pi over 2. If phi is pi over 2, that brings me down to the xy plane. And if I'm down to the xy plane, what points am I missing? I'm missing the entire southern hemisphere. So one possibility is phi goes all the way down to pi. Does phi have to go all the way to 2 pi? No, because I'm going to then have theta spin around. And so since theta is going to go from 0 to 2 pi, I don't need phi to keep going past pi because I'm going to get the rest by theta. So 0 less than or equal to phi less than or equal to pi, and then 0 less than or equal to theta less than 2 pi. And so again, if you look at what's coming down here, I come down, and now I'm going to spin around here parallel to the xy plane. And hopefully the easiest question of all semester, what kind of objects do you think spherical coordinates are good for? Spheres, right? You really can't hide what you're trying to do. Gee, I wonder what coordinates I should use for a problem that involves integrating over a sphere. If your function only depends on your distance from the origin, then that tells you, polar or spherical coordinates would be very good to use, because it means then the theta and the phi doesn't really matter. And so I can write my function many different ways. I can write my function as a function of the Cartesian coordinates x, y, z. I can write it as a function of the spherical coordinates rho, phi, theta. And I might have a situation where if only depends on rho, then you could have some function f of x, y, z would be f of rho sine phi cosine theta dot 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 dot, and then that might just equal some new function g of rho. So this is extremely useful. I might have a situation where my function only depends on the distance. So rather than looking at it as a function of x, y, and z, I can look at it as a function of rho, theta, and phi, and I can now reduce to a one-dimensional function to study. And that's often a lot easier we can then just use simpler techniques to handle what's going on. We always want to split things from a complicated problem to a simpler problem. If you can ever pull things out, that's great. All right, so when we're looking at this, are there any uniqueness issues? Does rho theta phi give me a unique XYZ? Does XYZ give me a unique rho theta phi? What do you think? Are there any issues with uniqueness? So will I always have one and only one X, Y, and Z if I give you rho theta phi? Will I always have one and only one rho theta phi if I give you X, Y, Z? Yes, so the origin is still going to cause trouble because I then go out no distance. How much do I go down for phi? Oh, I can go down anything for phi. How much do I spin around? I can spin around anything for theta. So the origin is going to be bad again. And so for a lot of things, it's annoying when we don't have uniqueness, when we have more than one thing that could work, but it's only at one point. For those of you doing physics, you've done gravity, the force is proportional to 1 over r squared. Where's the danger point when you're trying to do gravity? No, the danger point. When you're trying to calculate the force, what's the point that you have to stay away from? My force is proportional to 1 over r squared. What's the value of r that's problematic? Yeah, 0, because that means you're actually at the same place as the object that's exerting a force on you. Are you ever going to be at the same? No. So we don't really have to worry about the non-uniqueness breaking down because physically we're not going to be at that point. So it's not a huge deal that the uniqueness breaks down. The next question is, why are we choosing rho, theta, and phi as our variables? Why is rho coming down from the z-axis? Well, the reason is once I come down from the z-axis by phi, I've got some point over here, and I can look at the projection of this vector down into the xy plane. And I can look at what is the length. Well, if this is rho over here, then the z-axis component is just going to be rho cosine of phi. So the part over here, that length would be rho cosine of phi. And that's my z component. And now if I look at this vector in the xy plane, I've got my point over here. The amount in the direction along that is this. I can then ask, what's the amount in this direction, which is the same as what's down here. That's going to be my r. And so r is just going to be rho sine phi. So we get r equals rho sine phi. And now we can see why we've chosen to use phi coming down and rho and not r. Because what we now have is we now have polar coordinates in the plane. So r is going to just be rho sine phi, and now I have my angle theta exactly as before. That's why we didn't want to use theta coming down from over here, because then this would be phi, and it wouldn't just reduce to the polar coordinates we've seen before. So the whole point of using this choice is I now have polar coordinates for the pair r, which is rho sine phi, and the angle theta. Okay, so these are spherical coordinates. And again, we have our conversion factors to go back and forth between either one of them. Okay, if you forget which one is which, again, you try to draw the picture and say, okay, I'm coming down like this. Z is rho cosine phi, so my distance r is going to be rho sine phi. And now I apply polar coordinates here. And what you can see when you're doing polar coordinates is I can rewrite this as rho sine phi times cosine theta. That's just r cosine theta. I can write this as rho sine phi sine theta, which is just r sine theta. And so hopefully you can see, there's my polar coordinates. It's just the radius times cosine theta for x, the radius times sine of theta for y. I just have to remember that the radius is rho sine phi. Okay. So those are spherical coordinates. We've done cylindrical coordinates. We've done polar coordinates. We now want to figure out, how can we use this? So one of the things we're going to be studying a lot in this class is called level sets. And so this is going to be presented a little bit differently than the book, level sets. So the level set of f of height c is all inputs sent to c by f. So for example, let's say I have a bunch of mountains. I can draw, my level set is going to be all points that are a fixed height above sea level. And then I can just see, okay, well, which are going to be, the points that will be at that height. Okay. So can somebody give me a natural level set in this room? There's a couple of natural places. I'm sorry? So what, are you talking about like the height of the desk? Sure. So we could look at the height of the desk. That's a natural one. What else would be natural here? I'm sorry? Yeah, can you adjust your seats up and down? Are you able to move the seats up and down? Okay, so if you can't move the seats up and down, the seats would be another natural level set. Floor, natural level set. Ceiling, natural level set. And so when we're looking at, the spheres, the points that are at a specific height z, that's going to give you a circle that is just parallel to the xy axis at the height of z. And so depending on what function I give you, it will have different level sets. So for example, let's say I give you f of x, y, z is x squared plus y squared plus z squared. Let's calculate the level sets. So we want to find all x, y, z such that x squared plus y squared plus z squared equals c. So what's a really easy value of c to analyze? 0. What else is an easy value of c to analyze? Okay, what else? Go in the other direction. So -1. In fact, if I take c to be less than 0, what do you get? Are there any x, y, z such that x squared plus y squared plus z squared is a negative number? No. So you would get level set is empty. If I take c equals 0, what do we get? So what would be the level set if I take c to be 0? Yeah, it would just be the origin. And then last, if I take c to be greater than 0, what's the level set? So what would be the level set if c is greater than 0? So could you describe it geometrically? What is it going to look like for different choices of c? That's positive. Okay, but what would it look like? Can you describe it? It actually has a very nice name. So I want all points such as x squared plus y squared plus z squared equals c, where c is some number greater than 0. Yeah, it would be a sphere of radius squared of c. Is a sphere of radius square root of c. Because if I give you a sphere of radius square root of c, that's going to be all points such that x squared plus y squared plus z squared equals square root of c squared. And so there are really nice geometric arguments here in terms of what the shape is going to be. So another example, let's say I give you f of x, y is the sine of x plus y. What would be the level sets? Find the level sets of height c. So can somebody give me some easy ranges of c to analyze this? We'll be able to really quickly see what the level set is. Okay, there's something much easier than 1 though. Much easier than 0. Much easier than -1. What can you tell me about the values of sine? Where does sine live? Where is the output? Between 1 and -1. So give me a value of c where it's going to be really easy to analyze. 2. Right? If you give me 2, are there any x and y such as the sine of x plus y equals 2? No. -5? No. So case 1, let's say the absolute value of c is greater than 1. What can you tell me about the level set? It's empty. So it's the empty set. So if c is greater than 1 in absolute value, then you're fine. Now let's look at case 2. Let's say the absolute value of c is less than or equal to 1. And so once I choose x, I can then choose y, or I could choose y and then choose x. So I want to solve the sine of x plus y equals c. And then I can start trying to play some games. So if I fix x, let y equal arc sine of c minus x. Then what will the sine of x plus y equal? So I'll be taking the sine of the arc sine of c. What's the sine of the arc sine of c? It's just c. So if I choose a value of x, here's a value of y that will work. Is this the only value of y that will work? So is there only one value? If I fix x, I want the sine of x plus y to equal c. I'm sorry? So what else could I do? So when will two things have the same sign? I'm sorry? What do you mean by negative? Okay, so if the sine of alpha equals the sine of beta, then beta could be alpha plus some number of integer multiples of pi, right? That's one possibility. Think back always to the unit circle. So here's my unit circle. If I give you a value of sine, well, I could also take the corresponding angle over here. Well, I'm saying if I fix a value of x, I want to know what are all the different values of y that will work. And I'm going to just do this x by x by x. I could fix the value of y. I'm just marching down the x-axis. And for each value of x, I'm looking to see all the values of y that work. Well, it comes down to, I want to know when the sign of this quantity equals c. One choice is very easy. If I take y to be arcsine of c minus x, if I add x, the minus x cancels. I take the sine of the arcsine of c, I'll just get c. And then the question is, what could I add? And the whole point is sine is periodic. Every time I increase by 2 pi, I get back to where I started. So it's not just going to be y equals the arcsine of c minus x. I could add any multiple of 2 pi. The other thing we have to remember is if I have the angle theta, then if I look at this, which is going to be pi minus theta, that would also work, right? Those will have the same sign. My solution, y is equal to arc sine of c minus x plus 2 pi n. N is an integer. And I could also get y is equal to pi minus that. Plus, again, any multiple of 2 pi I. And so those would be all of the points that work. If you start to think about this, you'll see that there's going to be a lot of symmetry in how things look. Every time I increase x by 2 pi, what's going to happen? So what will happen if I increase x by 2 pi? Nothing. I get back to where I started. Sine is periodic with period 2 pi. Every time x increases by 2 pi, it's going to give me the same output. So a lot of times functions like this, you can have many different inputs giving you the same output. Over here, what we've noticed is for a given value of x, there's going to be infinitely many choices of y that will work. And so, it's a good exercise to try to figure out how to plot this and see what this looks like. So we'll probably put in a lecture next week on how to use something like Mathematica to actually just get a sense of how to plot stuff like this so that you can see it. It has a lot of really nice features to present information like this. So the level set is going to be very important. We're often trying to stay on the surface. We might be trying to stay on the surface, f of x, y, z equals some number c for some function f. And I'm only going to consider inputs that keep me on that surface. So if I want to be on the surface of a sphere, I want maybe x squared plus y squared plus z squared equals 1. And that will force me to stay on the surface of a unit sphere. Okay? All right, so any questions about this? Yes? 2 pi m with m an integer. So I could use n again, but I'm just trying to use 2 different dummy variables just to symbolize that there are 2 different sets of solutions. Okay, so these are level sets. And so now we're going to have ways of talking about various curves and whatnot. And so the idea is I'm going to want to stay on various surfaces. Depending on the surface that I'm looking at, some things are going to be easier to use in terms of representing where I am and what I'm doing than others. Okay, so any questions on the material we've done up till now? So your big thing today is the big 3 coordinate systems: spherical, cylindrical, and polar. We've talked a little bit about ellipses before. So let's see. So if I have to default, I always have my ellipses longer than. So here's my ellipse. And hopefully this will be somewhat familiar. Here's the foci at C and minus C. And it turns out one way of defining, what is an ellipse is it's all xy such that xy minus negative C0 squared plus the point xy minus the point C0 squared is constant. So an ellipse is all points whose sum of their distances from two foci is constant. Sum of the squares of the distances. Oh, no, so not squares, just their distances, not squares. All right. Does this look vaguely familiar from Algebra 2? We're not going to do too much with this, but how many people have seen something like this in Algebra 2? Oh, dear Lord, not too many hands are going up. Okay. We'll talk a little bit about ellipses. These are, the conic sections. You basically take a cone, and there are different ways you can slice the cone. If you have a plane slicing the cone parallel to the XY axis, you get a circle. If it comes in at an angle, you get an ellipse. You can get parabolas. You get all these wonderful stuff. And so the question is, how do you derive these formulas? And we get great formulas. Now, the first question, of course, is what is the distance? It says the sum of these two distances is constant. I claim that there's one point for x and y where it's going to be very easy to figure out what the distance is in terms of A, B, and C. Can anybody tell me what's a good choice to take for the point x, y? Zero B is one of them, and what else could you do? A0. So if we take the point xy to be either the point on the x-axis or the point on the y-axis, it's going to be easy to calculate the sum of the squares of the lengths. And so the whole point about something like this is if you want, imagine I have a piece of string and I tie it down at C and negative C, and I put my pencil here and I just move this around and it traces out a path. All right, so if I take xy to be at the point A, 0, the distances are going to be A minus C and A plus C. Yes? Well, there's a relationship between C, A, and B. And the relationship we will get is C squared plus B squared is A squared. So in this drawing, A is greater than B. And so the x-axis is going to be technically what's called the semi-major axis. The y is the semi-minor. No, I'm not going to have you too responsible for this. This is something you should have seen in Algebra 2. I'm just showing it to you today. If you are taking physics, stuff like this comes up when you talk about orbits of objects in the solar system. You'll get elliptical orbits, hyperbolic orbits, parabolic orbits. It's good to see this stuff once. So if the distances are A minus C and A plus C, what's the sum of the distances? Is A minus C plus A plus C, and what does that equal? That's just 2A. So now we know that when we're looking at things, if this is C over here, and this is B over here, that distance has to be A. Because we know that the sum of the distances has to be 2A, and those distances are going to be the same. So we now know A squared is B squared plus C squared. So now that we know that, if I give you an arbitrary point xy, we get x minus C squared plus y squared square root plus x plus C squared plus y squared square root equals 2a. And now we do algebra. And when the dust settles, you get x over a squared plus y over b squared equals 1. And this is one of the more common equations of an ellipse. So as a nice exercise, do the algebra. I'll make that extra credit. You can't look it up, but go, roll up your sleeves and do the algebra and show how this is equivalent to this. Are there any choices of A and B that would make this a really nice shape? Okay, so if both A and B equal 1, what kind of shape will you get? Circle. So more generally, for a given value of A, what would be a really nice value of B? It would be A. And so if you take B to be A, you get a very special case, you get a circle. And so in that case, we might just use a different letter. We might not use the letter A. What letter would we use? If A equals B, what letter should we use for that? R, right? X over A squared plus Y over B squared equals 1. Oh, that's X squared plus Y squared equals R squared. So the circle is a special case. Why is this useful? Well, let's say I give you X over A squared plus Y over B squared equals 1. I'm going to introduce some new coordinates. I'm going to let U be A cosine theta, and I'm going to let B be B sine theta. When I substitute and I look at X over A squared plus Y over B squared equals 1, this is going to become A cosine theta over A squared plus B sine theta over B squared equals 1. Does that work? Is that true? Well, this side is just cosine squared theta plus sine squared theta. Yes. Really? I just have a modification to my polar coordinates. In polar coordinates, I had x equals r cosine theta, y equals r sine theta. Now I just have u is playing the role of x, it's a cosine theta. V is playing the role of y, it's just b sine theta. An ellipse is very similar to a circle. And if I just change variables like this, I can convert my ellipse essentially to, circle. Okay? The whole point is, depending on what problem you have, different coordinate systems are going to be easier to work with than others. Okay, we didn't do this earlier. Spherical. We have x is rho sine phi cosine theta, y is rho sine phi sine theta, z is rho cosine phi. Okay. I always have to stop and pause because I learned spherical coordinates first from the physics department, and the physics department often has theta as the angle coming down from the z-axis, because for a lot of things, that's the angle that really matters. What would be the equation of a sphere in Cartesian coordinates? So, sphere of radius r. What would that be in Cartesian coordinates? Filled-in sphere. So what would be the equation of a sphere in Cartesian coordinates? Almost. No, I want a sphere, and I want the solid filled-in square. Less than or equal to r squared. And then in spherical coordinates, what would it be? So what would be the equation of a sphere in spherical coordinates? You know, solid filled in sphere in spherical coordinates. Well, we have to do our conversions. What does x squared plus y squared plus z squared come? What does that become? It just becomes rho. Is it rho or is it something related to rho? It's not quite rho. What's x squared plus y squared plus z squared? Rho squared. So you get rho squared is less than or equal to r squared, or it just becomes rho is less than or equal to r. That's the equation of a sphere of radius r in spherical coordinates. It's a really nice, simple equation. There's a couple of ways you could do this. You could square each of these and add. And when you square this, you get rho squared, rho squared, rho squared. Okay, I can pull out a rho squared. That's not so bad. Sine squared phi, cosine squared phi, sine squared phi, sine squared phi. Oh, cosine squared plus sine squared is 1. That drops out. I'll have sine squared phi plus cosine squared phi. That drops out. So if you substitute, roll up your sleeves and do the algebra, you will see that when I plug these in, this equation x squared plus y squared plus z squared, that just becomes rho squared. The other way is, what does x squared plus y squared plus z squared represent? It represents how far are you from the origin? Well, that's what we're defining rho to be. Rho is my distance from the origin. So this is just rho is less than or equal to r. In spherical coordinates, if I were to draw this, you know, it would look something, you know, like this, right? I'll even draw it like this and do it 2 different ways. Here's my sphere. Okay. What is the sphere going to look like in spherical coordinates? If you're not sure, well, you can guess. What does a circle look like in polar coordinates? A circle became a rectangle. What would you guess a sphere becomes? So a sphere can't become a sphere can't become a square. Go for it. Okay. Rectangular prism, a box, right? Shipping package, right? It's just going to become a box. It'll just be like this, right? Because if you think about what's going on, you're 0 less than equal to phi less than or equal to pi, 0 less than equal to theta less than 2 pi. Those are just free to move. And then rho is just at a fixed height. And then if you want the solid filled-in sphere, it's going to come down all the way like that. So in spherical coordinates, the sphere becomes a box. And a box is a very easy object to work with. We can chop up an interval, you know, a line segment, into a bunch of smaller line segments. They all have the same property. You know, a line segment is made up of other line segments. Is the circle made up of other circles? No, circles don't fit together nicely, but rectangles do. I can chop up a rectangle into smaller rectangles. And that's one of the whole reasons why we're doing all of this. All right, so I think this finishes off the chapter. I'll double check. We've now done the big 3, the big change of coordinates. We've talked a little bit about level sets. There's a lot more in the chapter than we're going to cover in class. For the exams, if you're fine with what we've done in class, you'll be fine on the exams. I'm not going to quiz you on minor things in the books that I'm not doing in class. All right, so this is a good place to stop.